This video will just be a relatively short follow-up to a previous video I had on solving differential equations. What I would like to take a look at are separable differential equations, where solving will require use of the natural log function and the exponential function involving base e. And here's the situation we'll look at. The derivative dy over dx for a given function is directly proportional to the value of that function, and our goal is going to be to find the general solution y equals f of x to this differential equation. Now that wording might not be something we see every single time, but the wording is very particular to one type of function. When I say that the derivative dy over dx is directly proportional to, that means that it is equal to some constant times the value for my function. And this just goes back to topics in Algebra 1 and Algebra 2 regarding the idea of direct variation. So that's a little bit of built-in algebra review. Now we're going to proceed with solving this differential equation, which is back to the calculus that we've been working on. In order to solve this differential equation, we're going to first separate the variables. And I'm going to do this in two steps. First thing, we'll separate the dy and dx by multiplying through by dx and getting dy equals k times y times dx. And now what we're going to do is get rid of the part that we can't have over on the side with dx, that y variable. And we'll end up with dy over y equals k times dx. And keep in mind throughout this problem, k is just a constant, so work with it like we do any constant. Step 2, antiderivative of both sides. For the left side, the antiderivative of dy over y, well, that's our natural log of the absolute value of y, equals the antiderivative of k times dx. Well, the antiderivative of any constant is just that constant times the variable, and then we'll put our plus c on this side. And now, finding the general solution y equals f of x, we need to solve for y. And in order to do that, I need to get rid of the natural log from in front of the y. Well, that is done by taking e and raising that to a power of natural log of y. And if I do that on the left side, I'll do that on the right side. These two inverse functions will cancel, and here we'll be left with y equals e to this entire kx plus c. And note here, the absolute value is no longer needed because it would allow two y values for one x value, which would make this not a function. Same way in that if we were taking a square root and we ended up with a plus minus, we could only have one or the other. We couldn't have both a plus minus and still have a function as our final answer. Now that looks pretty good. Y is by itself. It's equal to e to the quantity kx plus c. There's a little wrinkle in this that we can take a look at. And that is, if we think about reversing some common exponent laws, I could break up e to the kx plus c to be e to the kx times e to that constant c. Because multiplying two powers of the same base requires addition of the exponents, I'm just breaking it back apart into two different powers on this base e. And when I do that, think of what e to the c will actually represent. E is a constant, about 2.71, being raised to another constant. That is just one big constant. And so how I can rewrite my final result is y equals my e to the kx times a big constant c. And what the final result in this particular case, and in most cases where we end up with y being represented by an exponential function, this is a general model for exponential growth or decay. Growth when that k up in the exponent is greater than 0, if we recall that from previous courses. Decay when that k value is less than 0. And so working through a problem like this just serves to do a couple things, getting us to a point where we can say that we are comfortable with natural log coming up in a problem, e to some function plus c becoming c times e to that function, and y, the absolute value on a y, is not necessary. 3 common situations that pop up when we solve first-order differential equations, working from the first derivative of a function y in terms of x. Short video for this idea, but a few big things that will really help round out your knowledge on how to solve differential equations. And that's all I got, so thank you for watching.